this down. All right. Usually like to stream straight to LinkedIn. It's a good place to stream.
Yep.
Though this time of day, we'll see if anybody's logging in. But I'm back. I'm back for the second one. We're live streaming, so that's good.
Oh, nice.
Cool. Let's get going.
All right.
All right, man. So I'm here with Paul Hager, one of the authors of an intriguing paper titled Best of Both Worlds: Multimodal Contrastive Learning with Tabular and Image Data. In this work, Paul and his team tackle the challenge of utilizing images and tabular data in a self-supervised contrastive learning framework. This is a significant leap forward as it allows for the training of unimodal encoders that can leverage the richness of both data types. The team's approach ingeniously combines two leading contrastive learning strategies, SimClear and SCARF, creating a solution that is both simple and highly effective. They put their framework to the test by predicting the risks of myocardial infarction and coronary artery disease using cardiac MR images and a wide array of clinical features from a large data set of 40,000 UK biobank subjects. They also demonstrate the versatility of their approach by applying it to natural images using the DVM car advertisement dataset. One of the key findings in their research is the outsized importance of morphometric tabular features, which describe size and shape during the contrastive learning process. These features significantly enhance the quality of the learned embeddings. They introduce a novel form of supervised contrastive learning, which they term label as a feature, or LAAF, where the ground truth label is appended as a tabular feature during multimodal training. This innovative approach outperforms all supervised contrastive baselines, and the results show that the multimodal pre-trained model substantially outperforms all other models across all tasks and fine-tuning strategies. And if a lot of that didn't make sense to you, do not worry. We're going to dig deep into this and get all these terms kind of defined for you. But Paul, thank you so much for being here, man. Appreciate you.
Thank you so much for the invite, and yeah, I'm looking forward to some good discussions.
So I always like to kind of kick off the conversation with like some background knowledge. Like I mentioned, there's so many terms in there that were difficult for me to even say. But just to kind of get the listener up to speed, so they can kind of better understand your work and research, and
Yep.
walk away a little bit more educated. I'd like to kind of start with some background questions. So in deep learning, how does the nature of data, tabular versus imaging data, or tabular versus, we'll just say, unstructured at large, how does that influence the choice of learning algorithms and the overall approach to model training?
Yeah, well, so that's a really good question because, I mean, especially if we're talking about, a lot of us in the community, or especially in the computer vision community, we deal a lot with imaging data. Now everybody knows about text data and how to handle text data. There's been a lot of progress and advancements there, from ResNets to transformers to now large language models. But tabular data has always been kind of historically um, not as utilized in the machine learning community or in the deep learning community, because it's the machine learning baselines that we have there, from random forests to XGBoost, gradient boosted decision trees, these kinds of things, they perform so well and are so robust and are so fast that almost all modern deep learning solutions on tabular data just don't work quite as well as these classic algorithms that were developed years and years and years ago. So it's a big challenge. There's lots of papers out there, kind of, that try to tackle this now, but they always struggle with tabular data. And so it's really a key challenge how to incorporate this into a learning framework, and how to make it really work with something also like images.
So pre-training is something that's like a crucial step in many deep learning workflows. If you can kind of discuss its significance and its impact on the model's subsequent performance.
Right, so for us, especially in the medical domain, pre-training is super important because we often deal with very, very low data regimes. If a doctor in our hospital, so I'm working with the Klinikum Rechts der Isar in Munich, and if a doctor from our hospital comes and he's like, oh man, I have this crazy new data set of these pancreas cancer patients, can you see what you can do with that? I'm like, sure, how much do you have? And he's like, oh yeah, I got 50 samples. And for us, it's like, okay, if you think about deep learning, what am I supposed to do with only 50 samples? So for us, especially in the medical community, it's essential to have really strong pre-trained models that um, through this kind of self-supervised learning from other data sets from larger cohorts have already extracted so much information that with very few samples, which is also something that I show in my paper, we can still achieve, only maybe like a 4 or 5% drop in performance from the absolute max. And I think that's definitely going to be a paradigm going forward, and it's quite important as we, adapt these models to so many different regimes and different settings.
So I was curious, if you're working in a low data regime, does that mean like the model that you're going to use for fine tuning needs to have more parameters? Like let's say you got like the small, medium, large version of some pre-trained model. Would you then have to stick with using like the large model if you're working on a small, low data regime?
That's an interesting question. I hadn't really investigated it in the concept of model size. I mean, you definitely want to stay as small as possible, especially if you're not going to be doing a lot of pre-training, because I mean, at some point with a few amount of samples, even if we're just talking about like 1,000 samples or something like that, these models overfit so fast that it's so hard to, even through fine tuning, it'll just memorize whatever data distribution you have there and not really adapt and generalize to anything new. So there it is typically a good idea to keep it quite small. But I mean, what we're also seeing in kind of in the area of large language models or foundational models is that if the model is really, really large, maybe you don't want to retrain it with new data when you're adapting it to a new regime, but just give it some few examples from a different setting, and it'll be able to take that into account and adapt with some kind of few shot learning or something like that. And that typically works quite well more with the large models. So you're more maybe looking at p-tuning, prompt tuning, these kinds of things, and you don't want to specifically retrain the model. You get these kinds of catastrophic forgetting effects and stuff like that, and you just use that as a prompting strategy.
Can you define catastrophic forgetting for us?
So I'm not a huge large language model expert, but as far as I understand it, catastrophic forgetting is that if you have this pre-training objective, and you've trained over this massive corpus of data just with this pre-training objective, and then you fine-tune on a very specific task, it ends up forgetting a lot of these very generalized, well-conditioned features that it's very laboriously learned over this large pre-training objective, which ends up especially um, kind of reducing the performance of your model and reducing the generalizability. So they've even shown that with like ImageNet models and stuff like that. And CLIP was really the first model to kind of show more generalizability and get rid of this fine-tuning forgetting problem.
Does that kind of phenomenon happen in like the vision domain as well? Is there like an analog to that?
Yeah, so I think the closest analog is CLIP. So I mean, there's some work I think even in CVPR this year of CLIP when you pre-train it is quite generalizable. The linear probing accuracy of it on ImageNet and Sketch ImageNet and Toy ImageNet is quite good and quite robust compared to all other previous robust. I think Ludwig Schmidt has some very good papers on this. Um, but then as soon as you fine tune it on a specific type of ImageNet to maximize your performance a little bit, then you end up overfitting on that specific task and reducing your generalizability performance. And so now there are papers out there about there are some basic strategies that you fine tune it and you take the generalized model and you literally just take half of the weights of each model and add them together. That even works, some very basic approaches. But there was also some work at CVPR this year on how to like combine these models so that they keep the generalizability, uh, fine tune well on the task of choice, and don't forget all of those good features that they've learned so laboriously.
Awesome. Thank you for that. That's insightful there. So you mentioned self-supervised learning.
Yeah.
If you can kind of just briefly describe what that is and what's like the main difference between self-supervised and just like supervised or unsupervised learning.
So I think self-supervised learning is just the new term for unsupervised learning, as far as I understand it. The community used to talk about something like unsupervised learning, um, but kind of came to the conclusion that no matter what you do, you always have some kind of a supervision. I mean, or else the models don't learn anything. So self-supervised learning is more about creating the supervision yourself out of the data, with maybe some form of pseudo labels or some form of clustering. So you have like deep cluster from Meta, or you have now SimCLR, or masked autoencoders that are kind of like the modern paradigm of self-supervised learning in imaging. And the point there is we have now images and we want to learn from them without any labels. So supervised learning is okay, I have some data, I have a task, I put the data into the model, I get a prediction out, and then either it's wrong or it's right because I know what the label is, and I use that to give it a signal. I minimize that error, and I use that then to train my model weights. Well, in self-supervised learning, we kind of want to get away from, okay, just being good at this one thing, that like, okay, cats and dogs, but what if we just want to generally learn what is an object? So for that, we need to train from very, very large amounts of data, and what we found is this also makes it generally a bit more generalizable, a bit more robust. That's why you kind of get these very quick adaptations to new domains, or you kind of get, this very robustness of a clip of what I was talking about before. And so for self-supervised learning, I mean, the paradigm is you have a data point, you do something to that data point. In like for SimCLR, you would augment it heavily 2 times, and now you've basically created two views of that data. And because you created the views yourself, they come from the same source. So now you give them the pseudo labels, right? These two come from the same source. I give them the label 1. And then you have another image in your batch. You do the same thing. You give them the pseudo label of 2. And then the embeddings that you get when you put them through some kind of an encoder, you say, okay, well, because I handled the data myself, I know which data comes from the same source. So now I'm going to create my own matching game. I'm going to have these try to match each other, the 1s try to match each other, the embeddings of the 2s try to match each other, and the 3s try to match each other. And that's kind of like the SimCLR approach. Or you have something like masked autoencoders, where you take portions of your image, you create tokens out of them with the transformer, then you mask those tokens, and you then repredict those tokens, and then reconstruct the image. And so all of this doesn't require any labels, and when you have a lot of data, it allows you to basically get to the essence of an image without ever actually telling it what it is. And so you kind of create, a latent space, and hopefully, if your task is selected well enough, then you start seeing groupings within your latent space. So then all the cats and the dogs are maybe on one space, and the planes and the boats are further on the other, because there are some certain shared features, not all, but some, that kind of start forming this latent space and allows you to distill knowledge. What is an object? What is a cat? What is a dog? Without me telling you it's a cat or it's a dog.
Awesome. Thank you for that. That's very, very helpful in kind of understanding that, and I know the audience is taking away a lot from that.
Mm-hmm.
So we talked. I guess we talked. You explained pretty well what self-supervised learning is, and something that I think kind of goes. I often hear it in the same sentence, or maybe the next sentence, is contrastive learning.
Yeah.
And this is your papers,
Yes.
dealing with this topic as well. So, can you give us an overview of what contrastive learning is, and why do you think it's gaining so much traction in the deep learning community?
Right, so contrastive learning is exactly that SimCLR approach that I was talking about. So there are other forms of contrastive learning, and of course, you go from like triplet loss to SimCLR to maybe the more fancier versions of it. But the same concept is always the same, is that I have objects, I create different views of them through augmentation. Uh, Especially different contexts. So if I take a dog and I take a view of just its face, and if I take a view of just its tail, I've now created these two views, and I want them to capture the same essence of dog. So a dog should be recognizable from its head, or from its tail, or from its legs, or from its body, or anything like that. And then so I have these two views, and I pull them together, is kind of the lingo that they use in the contrastive learning community, and I try to pull those embeddings together, and then I contrast against everything else in my batch. And so then all of the other images that I have in my batch, I do the same thing. I create views, but I try to push them apart in the latent space by maximizing the similarity of cosine embeddings, the cosine similarity of the embeddings. And that's precisely then what I guess where the word contrastive comes from. You're contrasting basically the views between the images in your batch. Yeah, and I think it's gaining so much traction because it just works so well.
Yeah.
I mean, it's just been able to really advance so much of the state of the art in this kind of few shot, one shot, zero shot learning. It's very robust, so and it's very versatile. So it also allows you to do multimodal contrastive learning, which is, CLIP was the first one. I should say I come from the medical community, so actually Convert, CONVIRT, was CLIP even cites them in their paper, was the first to kind of do this with radiology reports and chest X-rays, where you do contrastive learning, but instead of taking two views of an image, you basically create your own labels by saying, okay, I have two modalities of one subject or of one entity. So in CLIP, it's an image and its caption. In Convert, it's a radiologist report and the chest X-ray, and then so instead of saying, okay, I'm gonna have to augment these and pull them together, I'm gonna say, I know that this image and this caption, they come together, so their embeddings I'm gonna try to pull together in the projection space and push against everybody else in the batch. And so this works fantastically well. I mean, you saw how much in CVPR was based off of CLIP.
Yeah.
It's
Yeah.
really taken by storm, and I mean, it's a great way of also aligning, imaging spaces, bringing language into imaging models, or using that to prompt imaging models and kind of get how do you bring these spaces together and how do you tie these concepts together. And it's a very, very robust and high performant way of doing that. So I think that's why it's quite popular.
Yeah, it was a huge part of a lot of the conversations I was having with people. Clip,
Clip,
just
clip,
kept
clip,
all
clip, clip.
over.
Yeah.
So I'm curious, just that if you can briefly give us like an intuition. You mentioned this mechanism of pulling and pulling, kind of like the intuition of how we're pulling together and how we're pushing apart. You said maximizing cosine similarity. Yeah.
Exactly. So I mean, so what you do is you have, in the case of CLIP, let's take it, you have an image and its caption, right? And so you have an imaging encoder and you have a text encoder, and these create embeddings. And these embeddings are the ones that you care about, and that's what you use for your downstream task. But then to kind of maximize, you have some amount of mutual information between these two entities, right? Because they come from the same subject. So if I say this is a picture of a dog, and it's really a picture of a dog, that means something. The word dog in that case, and the word picture, means something and share some amount of mutual information with the image that I have there. So we encode them, we get our embeddings, and the embeddings we project with just like a 1-layer or maybe a 3-layer MLP to a lower dimensional shared embedding space, a projection space. And this projection space is where we do our pulling and our pushing, and we do that by doing this cosine similarity, by calculating the cosine similarity between all embeddings across modalities. So you take basically all of your imaging embeddings and all of your text embeddings, and you calculate the cosine similarity of that dog picture with all of your text embeddings or the text projections. And then you try to maximize it so that it's most similar to the phrase, this is a picture of a dog.
Okay.
And then this is what then starts bringing these semantic concepts together. Then you have multiple pictures of dogs and then planes and trucks and people and everything like that. And then this is what starts to then give a signal to the encoder that it needs to encode the mutual information that is shared between the sentence, this is a picture of a dog, and the actual picture of the dog. Exactly, and then that's how you start pulling that together and getting these well-conditioned encoders.
And we're talking about embedding spaces and all that just right now. Can you kind of give us a just a little bit more intuition of this concept of embedding spaces, and how does this serve as a bridge between raw data and high-level understandings that a model develops?
So embeddings is kind of a lower dimensional representation, or maybe a higher dimensional representation of your data that tries to capture the essence of it. It's going to capture many different aspects of it, sometimes spurious aspects, sometimes important aspects, and it should kind of allow you to understand what this is. You can have high-level semantics, global semantics, low-level semantics, basically regional semantics. So some of these models are more going to give you more global embeddings, something like SimCLR. This will more help you with like a global classification. Others will give you more localized embeddings, which is important if you want to do something like segmentation or something like
Mhm.
that. And so it's a way of distilling knowledge at the end of the day, so that you can very quickly adapt in maybe just, with just 2048 dimensional vector to whatever task you have without having to extract that knowledge from the image first.
Awesome, thank you. And you talk about mention it in the introduction there, this concept of a unimodal encoder.
Yeah.
Um, so I think intuitively I can probably unimodal in there. So are we just taking multiple modalities and combining into one modality? Like what does this mean? What does
So in this context, unimodal means that to generate this embedding, you only need one modality. And so this means that the multimodal aspect of our model is only during the calculation of the loss. So if you do fully supervised multimodal training, what you would sometimes do is you would, fuse your data, or you would create an embedding and fuse your embedding and then keep learning with that fused embedding. And what this requires, though, is that whenever you're in the wild, if you want to make a prediction, you need the caption and the image. Or if you're in my case with my paper, if you're in the hospital, you need the image and all of this tabular data. But oftentimes we don't have that. We don't have the time. We don't have the resources. Or you just simply want it to work with only the one modality. So I think what's quite important is to maintain the ability to train these unimodal encoders. So we only do the multimodal kind of on the level of the loss, which allows us then at test time to pick and choose. Do I have an image and text and table? Do I use all three? Because I can still always concatenate my embeddings however I want. Or do I only have an image? And so this model still remains useful for me because I only have an image and it still works. And because I trained it multimodally in the pre-training, it's still able to incorporate that secondary signal from text, from tables or whatever, and it has increased its performance in the unimodal setting.
Awesome, thank you. Let's dig a little bit more into your research paper. I think that's got some good background
Yeah.
context now. So in your research, there's a unique aspect of combining SimClear, SimCLR, and SCARF. Can you kind of just, explain what these are, and then yeah, we'll take it from there. Like,
Yeah.
give us an explanation of what these
Sure.
are. Yeah.
So I mean, SimClear is so I've been talking quite a bit about SimClear. It's this mainly I use it kind of for the augmentations and for the inspiration of the clip loss and everything like that. Scarf is also a self-supervised method for tabular data. I think from Google research, it's a quite good method, I need to say, in my experiments after training with Scarf. I typically outperformed the fully supervised tabular MLP. I forget how it performed compared to the XGBoost, but it's a strong method which I would recommend checking out if you have tabular data. And so what Scarf does, or like the main aspect that I took from Scarf, is how to corrupt the data or how to augment the data. Because I mean, if we have images, SimCLR kind of does, it does a flip, it does grayscale, it does maybe intensity shifts, and this makes it so that the information you learn from the image is irrespective of these aspects, right? You want it to be robust, so that you don't want it to care about if your color is in black and white or fully colored, or if you're looking at the face of the dog or the tail of the dog, you want it to just distill what is a dog. And you need to do that for the tables also. You don't want it to overfit just on these exact tables that you have. You want it to learn more generalized features. And so Scarf handles that by doing what's called, they call it corruption, where they take a part of the table, 20, 30, 40, 50% of each batch, and they randomly select columns to be sampled from the empirical marginal distribution, which means just you take basically all of the valid values for this column. So let's say one of my columns is weight. So I have now a vector of all of the weights in my entire data set. And to augment my sample in the data set of weight, I would replace my actual weight with a random weight that exists within my data set. So you're not creating new information, you're not creating information that doesn't exist, but you are creating maybe nonsensical combinations, because each of us has a certain profile. So somebody that weighs or somebody that doesn't smoke but then maybe smokes multiple packs a day in a different question. So sometimes that doesn't quite add up. But what this does, it doesn't it forces the model to not overfit just on a single column, but take the entire tabular data as a whole to learn a representation. And so I basically combined the augmentation strategies of both of those. And then, as I was saying with CLIP, you encode them, you project to a common latent space, and then you do this CLIP loss across the modalities.
Is Scarf like is it implemented in Python like or
Yeah,
the
yeah.
where's
So
the yeah.
it's implemented in, I think, yeah. They I don't know if they have code. There's a PyTorch implementation of Scarf
Okay.
out there
Okay.
that I use as a basis for my work. I also have an implementation in my paper, so you can also check that out.
Yeah.
It's quite simple, and it works very very well.
I'll have to give it a try in some Kaggle data sets one of
Yeah,
these days.
yeah,
Try to test it
yeah.
out. So can you kind of go into the thought process that led to this integration, and what is it about this kind of combination of these two that leads to your model's performance?
Right. So this came about because in the clinic. So I come from the clinical kind of medical domain, right? And so for us, we often have a lot of very unstructured data. And for us, that can be anything from patient age, weight, blood pressure. Maybe they've taken some blood work. You have, continuous variables in these biobanks that are like these rich sources of information that the UK, for example, or even in Germany, they have somebody come in for a day and they do like an entire day's worth of tests. They have you run around the block, they have you take eye tests, hearing tests, all these kinds of things, and they have such rich data in this. They have 1,000 tabular features in there, and all of it is quite unstructured. So sometimes you have continuous variables, sometimes you have categorical variables, something like how do you smoke, how much do you smoke, do you drink, how much do you drink, do you eat red meat, do you eat fish, these kinds of things. And so we needed to find a way to use this information to more intelligently interpret our images, because at the end of the day there's only a certain amount of image information that is kind of captured in this image, and your health is a lot more than just a scan, right? Your health is also what you do, the life choices that you make, or maybe some of the the genetic predispositions you have. So we're looking at ways of bettering the ways that we interpret these images based on these other modalities. So I mean, an example is somebody with a very large heart could be very large because they do a lot of sports, and so their heart is very well trained and constantly pumps a lot, and so it's grown in size, kind of to it's a muscle, it adapts to that. Or because the heart is quite large because the person is very overweight, and so their arteries are quite clogged, and so it needs to pump extra hard to make sure that the blood gets to where it needs to be, and so it grows in size. But somebody with a very large heart because they're overweight, or somebody with a very large heart because they do a lot of sports, do a lot of running, has a very different health profile, and has a very different effect on downstream classification. So we want some kind of an external data source to aid the imaging encoder in how it interprets these images, and that's why I kind of fell to CLIP, because it's a great way of doing this and still having strong unimodal encoders that at the at test time when I'm in the clinic, sometimes the doctor just takes a scan and needs to make a decision right away. He can't do an entire day's worth of tests with every patient that comes in.
It's awesome, man. So like it's just saying. So you have like a scan, like you mentioned, a scan of a heart. Like it could be potentially these two scans. I don't know what they're called in the medical.
Cardiac MRI,
Yeah,
yeah, MRI
yeah.
scans.
Okay, so you can have two that look exactly the same, but one heart is two large hearts. One guy's healthy, one guy's fat. But without having that extra tabular data, like you can't really discern the two. And this is
So what could happen is that you end up kind of just clustering together in your latent space. So I mean, there's a debate to be had about if feature disentanglement exists, and how much we can kind of like interpret into this. But the way I sometimes think about it is, let's say you have a region of your latent space that's dedicated to the size of the heart, right? And if you only had this feature of an imaging encoder, it would just group all of the large hearts together. But if you have a secondary source of information during the pre-training process, it can create subspaces within this large heart space. So a part of your feature space is dedicated to the size of the heart, and now you can create a subspace for large hearts from healthy patients and large hearts from overweight patients. And then in your downstream tasks, when you're doing like your hyperplanes and you want to classify who's sick, who's not sick, this improves embedding performance.
Awesome, thank you. So I think let's jump into now this concept of label
Hmm.
as a feature,
Yep.
LAAF. Just kind of briefly give us an intuition or explanation of what this means.
Right, so this comes from the supervised contrastive learning setup, and so this came from the fact that so we had done our analysis. We showed okay, we can train multimodally, and our unimodal performance is stronger. It's stronger than training with only images, stronger than SimClear, BYOL, SimCM, Barlow Twins, all of these different things. And then we wanted to try to find some ways of really taking advantage of the uniqueness of the tabular data, right? Because not a lot of people work with this, so there's definitely some cool tricks that we can do now with the tabular data. And one of the things that we were thinking of is that if you do supervised contrastive learning, which is the setting where you say, okay, so I can do contrastive learning completely without labels, but sometimes I want to do it because I can train an unimodal encoder in a multimodal way, for example with CLIP. And I do have all of my labels. So is there a way of using my labels during the contrastive learning process? And that's this paper, Supervised Contrastive Learning, I think from Philip Isola, that basically showed you can use the labels during the contrastive learning process, that instead of pulling just my embeddings together, and pushing against everybody else, I can pull everybody of the same downstream class together. So if I have multiple dogs in my batch, I pull them together and I push against everybody else instead of pushing against the dogs, which doesn't make much sense because at the end of the day, I'm interested in classifying all the dogs together, and so I don't want to push against them. And so it's supervised because now I'm starting to use the labels during the contrastive training process, but this improves even over normal supervised training typically. So I haven't really seen a lot of cases. If you have enough data, usually supervised contrastive learning will outperform just plain supervised learning, because there's a certain degree of robustness that you get to this contrastive learning process, and this L2 normalization and spreading around a hypersphere. And so what we then decided, what we were looking at, is there a way that we can maybe in the supervised setting use the labels in a clever way? And what I came up with was, at the end of the day, a label is just a 0 or 1, or like maybe for my cars data set, I had 280 classes, so it's just a number. Or if it's a regression task, it's also still just a number or whatever. So you can just add it to the table. I mean, the table is fully morphable. I mean, it's exactly meant for representing numbers. And so you just add it to the table as a column, and then during the pre-training process, the model, it's just another feature that the model considers when forming its latent space. And this improves performance by itself. And the cool thing is that a lot of these supervised contrastive learning, like supervised contrastive learning, or there's another one called false negative elimination, they operate on the level of the loss. So they're changes to the loss, and my method is a change to the data. So it's fully complementary. You can add them together. So I combined also label as a feature with supervised contrastive learning to reach even higher highs, basically, and it's quite flexible in that regard.
That's awesome, man. That's gonna take me a a little bit of time to digest. I'd recommend you guys checking out the paper as well. Um, so I guess you kind of did give us. Well, my next question was going to be about the inspiration behind this idea, and I feel like we did kind of get that.
Yeah. So yeah, it's about, if you have something new, like in my case it was the tabular data, try to like really focus on that. There is something new to be learned with your specific case. If it's medicine, if it's tabular data, if it's maybe the robustness or whatever, or if it's an interesting data set or an interesting modality, think about how to best exploit the unique characteristics of that. And that's kind of like what I was doing when I was trying to think of a way of working with this tabular data.
Um, so your approach is quite generalizable, And you mentioned the DVM data set,
Hmm.
kind of like natural images, and DVM data set is a car advertisement data set. And so you're able to generalize to that. So can you talk about the challenges in ensuring this generalizability and how your model overcomes them?
Right. So these are two separate models. Oh, sorry. So these are two separate models. So one for the medical domain and one for the car advertisement. But what we wanted to show here was that this wasn't just a specific uh, case that's only works in medicine. I wanted to kind of show that it even worked better on the cars than on the medical data. And there I was able to really show. I mean, on the cars, you have these 280 classes, so it's a lot more well conditioned. You kind of have these typical things. In medicine, I only had one. I only had two classes, and I had severe label imbalance. So I had like 1% positive labels for the cardiac infarction or heart attack. So it was you always have like different dynamics depending on what is your downstream task, depending on what is the data that you're looking at. So it's always a new opportunity to kind of probe your method or your model or your approach and see, okay, well, what if we change like the data distribution, or what if we change from like a binary classification to a 280 classification problem? What if we go from medical data to natural images? Does this still hold up? And so that was a good way for us to kind of really test the limits of what we're working at, and it worked even better on the natural images, which we were quite happy with.
So we mentioned this kind of in the introduction, this word morphometric tabular
Yeah.
features, uh, and this helped improve the quality of the learned embeddings. What even is a morphometric tabular feature?
Right. So it's a bit of a convoluted word. Maybe another way of thinking it is an imaging derived feature, imaging derived or like imaging seeable feature. So the way we define morphometric features are those related to size and shape. So something that you can kind of directly see in an image. Um, and in the end, what we found is we did like an integrated gradients analysis, which is a form of explainability, where you take a null vector or a null image and you integrate the gradients of the function to your embedding um, along the straight line path. And what this does is it gives you for your individual features the importance of generating that embedding. And so in our case, if you have an image, it'll give you the individual pixels that are most important to generate the embedding. So for images, it's not really that good because sometimes you get adversarial pixels, and there are other more maybe a bit more robust methods for images. But for tables, it's quite powerful because if I get out at the end that the most important feature was this column, the column "do you smoke or not," was the most important feature for generating the embedding, that's going to be a semantic concept. This is something I can interpret, right?
Mhm.
Because I know what it means. Do you smoke or not? I don't know what this one pixel in the image means, but I know what this column means. So this integrated gradients approach is particularly well suited for tabular data. And what we found there was that to generate the embeddings after the pre-training process, it really focused on stuff that is like seeable or calculable from the image. So we were looking at like left ventricular, so like that's one of the ventricles in the heart, the mass or the volume, or the ejection fraction, so how much it can pump, or the weight of the patient. So you kind of see the fat around the heart in the cardiac MRI slice. And so these kinds of things were the most important features for generating the embeddings during the multimodal pre-training process. And I mean, it makes a lot of sense because what is the task of your model or of your loss? It needs to find the mutual information between the two data sources to maximize that cosine similarity, to make those projections as close to each other as possible. And so if you have something that exists in both your image and your table, like something like weight or something like the volume, or in the case of the cars, the top four features was the width, the height, and the length of the car, and the distance between the wheels. And so these are things that are immediately seeable from the image, and this is what allows the loss to really maximize the cosine similarity or minimize the loss. Um, And so so that's why these morphometric features are so important for this multimodal pre-training process.
Thank you. Um, so I guess let's jump into some of these. Well, actually, no. We should talk about the process of identifying these features and their impact on overall learning. I don't think we really touched on that.
Yeah, so maybe to the impact. So this is quite interesting, actually. It's a good question because what I really found also was that you need to be cognizant that pre-training is often separate from fine-tuning, or it is a separate step, right?
Yeah.
And your pre-training task is a very specific task. Like in this case, it's I have these two modalities. I'm trying to pull their projections together. And so I'm trying to look for that information that is present in both modalities. And if you dedicate too much representation space to that, all you end up having in your embeddings is that shared information. But there is some amount of unique information in each modality. If the modalities were exactly equal, there would be no point in doing this multimodal learning, right? So we want to dedicate enough of our representation space, of our features, to these shared features, which allows us to minimize our loss, which allows our pre-training to work well, to really learn interesting features. But we don't want it to suffocate the embeddings, because then all it learns is the common information. If I just wanted the common information, it's not optimal. There's still unique information to each embedding or to each modality. And so that's what I saw, like for the cardiac tasks. I tried looking at subsets of the features, right? I have 117 features. If I'd look at the subset of only these morphometric features, it's super easy to match them. I can see that if I look at the top one accuracy of matching the two projections. But the performance of the embeddings is degraded because all it focuses on is on this mutual information. But it throws away all of the unique information of the images that isn't present in the tabular data. And for the cars, on the other hand, I actually improved performance by slimming down to just 5 tabular features, which were the 5 morphometric features. And that shows you that, like, for the cars, that the car task of what is the name of the model of this car, it's so strong to understand how big this car is, like its length, its width, and its height. It's such a strong indication of the model of the car. Each car maker has a very strong opinion of how they make their cars. That this is very, very strong, and that some of the other information ends up distracting the model. This is another part of the problem with tabular data and deep learning. There's actually a good paper called, like, why does deep learning not work on tabular data? And what they found is that tabular data is not robust to spurious data, to inconsequential data, to random data. So they added columns to their tabular data that was completely random, total noise. And you would hope that an MLP, if it's total noise, there's no correlation with any downstream labels or whatever. They can guarantee that. That it just zeroes out those connections, right? There's no point in even looking at this column. But what the MLPs always end up doing is overfitting on that. They find some weird statistical correlation that doesn't actually mean anything, and they dedicate some of their space to that, and they let that flow into their calculation of the other nodes, and this ends up lowering your performance, which is why if you're working with tabular data, feature selection is essential. And those are the next couple of things that we're looking at now in the lab, and how to do this kind of feature selection so that you select both for the pre-training task, where something like morphometric features are important, but also be cognizant of your downstream task, where maybe it's not just the morphometric features, but some other features that are still quite important that you want to keep in there, because that's where you're going to get your performance from.
Awesome. Thank you for sharing that. Kind of get into some philosophical questions.
Yep.
While you're answering these questions, you'll see me type. I just need to let my next interview know to come up here.
Yeah, sure.
But
no problem.
as a researcher in deep learning, how do you envision the future of self-supervised learning? What is the future of self-supervised learning, and especially with this increasing availability of multimodal data?
Right, so I think we're definitely going to get more and more multimodal. I think that's the next big frontier, not just bimodal, but trimodal, quadromodal. At the end of the day, there's only so much you can learn from one modality. We want to learn what is the essence of an object, right? What is a dog? So I can show you a picture of a dog, but that's not going to tell you what this dog sounds like. I can describe a dog. I can maybe describe how dogs are usually very happy and they love to eat and they love to run around, and that will give you some new information, something that I couldn't learn from the image. And so it's quite essential as we go forward, if our goal is to learn what is the essence of this object, get more and more multimodal and really find clever ways of combining this information, which ties back to what I was saying of how do we combine it. We combine it in that we look at the commonalities, but we also leave room for the uniqueness. And that's really what it's going to be about going forward, is combining both the commonalities and the uniqueness of each modality.
So you're working in medical images,
Yeah.
highly regulated field,
Yeah.
explainability, super important,
Yeah.
and deep learning models are often criticized as being black boxes.
Yeah.
So how does your research address this issue, and how do you think the field can work towards more interpretable and transparent methods?
Oof. Yeah, that's a really good question. Um, so, I mean, my research tries to address this a little bit through the explainability that we look at, especially, I mean, we had the luxury of working with tabular data, which I was talking about before, has is high-level semantic concepts, so that if our model tells us one of these columns is important, that is something that I can go to a doctor with. I can say, okay, the model is focusing on these features, and that's something that that he can say, oh, okay, that makes sense. Those are the same things we see in the medical literature, which will increase the confidence in these models. Working forward, I'm sadly not too much of an expert in interpretability. I definitely think, I mean, it's the number one thing that we hear from doctors is like uncertainty and interpretability is for them key. Sure, maybe if we get to the point where it's like 100%, this will work. I think maybe something that's kind of maybe, I don't know if it's underexplored or if this even makes sense, but sometimes tools also exhibit patterns of when they work and when they don't work, right? And so if we get these tools into the hands of people, they could start to also form their own opinions. I'm not advocating that we start, running these in hospitals willy-nilly, but at some point, there's always going to be some certain failure cases for a model. And a doctor is going to have to understand when does the model work well and when does it not work well. And a lot of that is going to be calibration. A lot of that is going to be giving uncertainty. A lot of that is going to be giving basically highlighting why the model came to its decision. That's also going to be very important, but we are also going to just have to give the people time to adjust and understand in their practice, maybe not on, life critical applications right now, but on old data or something like that. Okay, so the model works really well in these cases, so I can maybe trust it a little bit more there and use that to lighten my load, but it doesn't work maybe in these other cases that maybe are a bit more difficult. So I'll spend more time as a doctor focusing on these more difficult cases. I mean, that's where we're trying to go towards, right? We're not trying to replace doctors, we're trying to make their lives easier. And if we can make them go faster on the easy cases and devote more time to the hard cases, I think that's definitely going to be a net positive.
So wrapping up with the final question here.
Yep.
So can you describe a moment or project where you grappled with the limitations of deep learning, and how did you navigate these constraints?
Yeah, all the time. I mean, it's like I said, medical imaging is super low data imaging is sometimes tabular data where really all you need is like an XGBoost. You try a deep learning model and it just doesn't generalize. It just completely overfits, and then you do a random forest that trains in 30 seconds and it outperforms everything that you've been working on for 2 weeks. And so you're like, okay, what do I do now? So you need to keep agile. You need to also go back to the basics sometimes. If something works, then it works. And then if a doctor comes to me and he needs a way of interpreting his data, or he wants a model that basically predicts X, Y, and Z, sure, I'll try an MLP on it, but I'll also try XGBoost, I'll also try a random forest, I'll also try these kinds of things, and if they work better, then they work better, and then that's what he needs. And so you can't, I guess, sure, deep learning has done some crazy things and some really, really good things, and I'm sure it's going to keep improving, but you also need to be, I mean, not too proud to go back to the basics sometimes, and just maybe just a logistic regression is enough.
Yeah. And I guess the follow-up question to that last one. So, these experiences, what have they taught you about uh, uh, balancing theoretical advances and practical implementation?
Right. So there's always crazy theoretical advances coming out. There's always so much cool stuff happening, and you always really want to try the newest thing because like you've seen this paper and it's revolutionizing. Transformers are revolutionizing language, or it's revolutionizing imaging. But at the end of the day, transformers are also quite data hungry. And so if I'm in medical imaging and I only have like 1,000 data points, it's probably not going to be enough to train a transformer. You need to understand why these things work. Maybe you can apply even some of the concepts, even if you don't take the method one to one, but you can think, oh, that's really clever how they solved that and that problem. And so you try to apply that to your own field or to your own work. But you can't just keep following the hype train from one to one, because oftentimes, maybe, I mean, if you're just doing ImageNet, sure, just follow the hype train, but that's not where the interesting problems are. So you need to be able to kind of like adapt to whatever's happening, and really think about how to best incorporate it into your work.
Paul, thank you so much for taking time to join me today. Where can people find you online if they wanted to get in touch?
So either email me, paul.hager@tum.de. It's also on the paper, the GitHub there, or I don't really have any social media or anything like that. So maybe LinkedIn if you're interested. Just search for me, add me. Yeah.
Awesome. Thank you so much for being here. I appreciate you taking
Thank you.
time. Awesome. Cheers, everybody. We'll be back in just a couple of minutes with Anish